In day number 2, we're going to be doing the limit comparison test. Now, this is different than day 1 when we learned about direct comparison. Direct comparison just said, hey, if you are a summation, we call you, A sub n. If you're larger than something that diverges, you're going to diverge. That's easy. And if you're less than or smaller than something that converges, you're going to converge. Maybe you noticed this on the homework, or maybe you kind of wondered it to yourself. What if you're smaller than something that diverges? Does that mean you're bad? Or does that just mean you're not the very, very best? Doesn't mean you're terrible. What if you're larger than something that converges? Does that make you a diverging series? Not necessarily. Think of it in terms of sports. If you think of Beechwood, think of our football team. Let's say we play Mentor or St. Ignatius and we lose by a field goal. That'd be a heck of an effort on our part. Does that mean we're terrible because we lost to somebody that diverges? No, not at all. Heck, if we're losing to those teams by a field goal, we're probably going to win our league. Similarly, let's say that we're playing somebody who hasn't won a game in the last 7 years. And we beat them, and we beat them easily. Does that mean we're going to have a good season? No. Just because we're greater than something that converges doesn't mean we're going to diverge. It just means we don't completely suck. Right? So we need more evidence than just a direct comparison in those situations. And that's what I wrote below. I wrote the limit comparison test is useful when the direct comparison test fails. Maybe you can't compare things easily with your normal geometric or p-series that we use. Well, then we go this route. What you do is you start off with something called a sub n, that is given to you in the problem. You make up your own b sub n. And again, you make up the b sub n. Usually you make it something that's either geometric or p-series. You turn it into a fraction, and you take the limit from chapter 1 as n approaches infinity. The limit's going to come out to something, and the book just called it L for limit. If the limit is finite, in other words, not infinity or negative infinity, and it's positive, then these two things, the a sub n and the b sub n, will both behave the same way. It reminds me a little bit of the integral test from section 9.3. They're either both going to converge, or they're both going to diverge. They kind of have an agreement with each other. They're going to stick together. All right, the best way to learn this is just to do some examples. I think it'll become crystal clear. At least I hope. That's my goal. Okay, number 5, use the limit comparison test to determine whether this converges or diverges, this series here. Well, I definitely don't recognize this as anything familiar. It's not geometric. It's not a p-series. The limit heads towards 0, so it doesn't automatically diverge by nth term test. You can't use partial fractions, just nothing. So at first I would probably think, okay, let's make a direct comparison. So I'll call this a sub n like I did yesterday and like you did on your previous homework. And for b sub n, I think a wise, logical choice would either be 1 over n or maybe 3 over n. I'll use 3 over n. And 3 over n, if you were to put a sigma in front of it, it diverges. In fact, it's a diverging harmonic p-series. Really, the harmonic p-series is 1 over n, but if you multiply something by 3, that's not going to change whether it converges or diverges. If you're not adding up to infinity, tripling something isn't going to suddenly take you to infinity, if you know what I'm saying. So I'm going to leave the 3 in. It's up to you. You can either leave the 3 in or you can call it 1 over n. Doesn't matter. What does matter is which way the symbol goes in the middle. In this case, the blue is going to be the larger one because the minus 2 is shrinking the numerator. The denominator is growing. If that hadn't been there, blue and green would be equal, but it was there. But again, here is the problem with using direct comparison test. Oh, bummer. We, right here, a sub n, are less than somebody who might win the state championship. They're awesome. All right, they beat us. And normally as a coach, I'd say, well, so it doesn't mean we're bad. We fought tough against those guys. Those guys are amazing. Those girls are amazing athletes. We're okay. So you can't just say, oh, we suck, we converge. No, we don't know. So we're going to break out the limit comparison test for the very first time. Okay, here's what we do. We call it the limit comparison test because we use a limit, hence the name, n approaches infinity. And what you do is you stack these two things on top of each other in a fraction. It doesn't matter which one goes on top. Usually we put a sub n on top. Rather than making this a monster fraction and saying green divided by blue, and then, oh, you're dividing by a fraction, let's multiply by the reciprocal. Let's just save time and we'll just multiply by the reciprocal on the fly as we write it. So instead of divided by 3 over n, I'm going to say times n over 3. Just a little bit of algebra there. All right, here's what's going to happen. If you were to multiply this out using distributive property, you'd have 3n cubed minus 2n over 3n cubed plus 15. Remember, we're taking the limit. It's a limit comparison test. We're taking the limit as n approaches infinity of this. If you put the infinities in and use a little L'Hospital's rule, I think you can see that this is going to come out to 1. And since 1 is finite and positive, it means that the limit comparison test works here. So green and blue have entered into an agreement, a treaty, if you will, that they're going to behave the same way. And since we already know that blue diverges, green's going to diverge as well. All right, once again, we have something unfamiliar looking. We'll call it a sub n. When I do this section 9.4, I'm always assuming at first that direct comparison is going to work. You'll know immediately whether it does or doesn't. So you're going to approach all these problems today just like you did yesterday. Figure out a good b sub n, try to use either a p-series or something geometric. I'm going to go with a p-series again. I'm going to go with 1 over n squared. Hopefully you can identify why I'm doing that. Seems like a good idea. And of course, I know what 1 over n squared is. It's a p-series that converges. All right, a sub n, because of the plus 9, a sub n is going to be larger. I mean, you could factor out the 4/10 first if you were uncomfortable with the fact that that was there, but clearly green is larger than blue here. So you're greater than something that converges. That means, you can beat up a first grader. Does that make you tough? Are you bad? Probably not. Okay, maybe you are. I don't know, but that's not going to prove anything to anybody. So we have to use limit comparison instead. And again, remember that the limit comparison test starts with a limit. Makes sense. All right, you just stack these up as fractions. I'm going to write the a sub n first. Divided by b sub n, or times the reciprocal. I think you can see that if you do distributive property there, you're going to end up with 4n to the 7th plus 9n squared. If you head towards infinity with the n, this limit is going to become 4/10 or 2/5. And 2/5 is positive and finite. So therefore, the original two a sub n and b sub n are going to behave the same way. Since we know b sub n converged, a sub n will converge as well. So that green is a converging series. How do I know? Limit comparison test. All right, a couple more. This is number 7. Again, if this did not have the -1, that would totally be geometric. It would just be 1 to the n over 4 to the n, which is 1/4 to the n. And I know that 1/4 to the n power is geometric, and that is a converging geometric series. So right now, they're absolutely equal to each other. But the moment you take 1 away from the denominator, they're not. This green, which again normally we label a sub n, is going to be greater than the blue b sub n. All right, so we're wondering about a sub n. We're greater than something that converges. That doesn't mean we're any good. It just means we're not the worst ever. Okay, so we need limit comparison test. Direct comparison test would fail there. It wouldn't be conclusive evidence. We start off the limit comparison test with, oh, you know it, a limit. The limit as n approaches infinity, as always. Of what, you ask? Well, a sub n over b sub n. Okay, again, instead of dividing, I multiply by the reciprocal. The 1 and the cute little 1 to the end, those are both 1s. They cancel. And you're left with that, which, honestly, if n becomes infinity, that's 1. And 1 is positive and finite. Therefore, the original one, the green, behaves the exact same way that the blue does. Since the blue is converging, the green a sub n is also a converging series. All right, let's do our last one, number 8. Oh my goodness, wow. Okay, I'm going to compare this to 1 over n to the 2/3. Which I realize is a diverging p-series. We'd always have the option to kick the 5 out, all the way out front if we wanted to. Let's say the 5 was out front and the +6 was not there. These would be absolutely identical. But with the +6 being there, it weights the bottom down a little bit, which makes a sub n a little smaller than b sub n. B sub n is going to win this war here, at least with the 5 being outside. So a sub n is smaller than a diverging series. That doesn't mean that it converges, it just means it lost to somebody. Maybe you're going to go 9-1 this season. It doesn't mean you're terrible, it means you're still going to the playoffs. We need limit comparison once again. Let's bring this over here. It's limit as n approaches infinity still. And now if you combine forces here, you got 5 times n to the 2/3. On the bottom, you got n squared plus 6 to the 1/3. We have to figure out what that is. That will come out to 5. I'm going to prove to you that it comes out to 5 in a moment, but it will come out to 5. And that 5 is positive. And it's also finite because it's not infinity. And so limit comparison test will work. And since the blue diverged, the green is going to diverge as well. So let me write that answer. Again, on your tests and quizzes, don't write LCT. Don't go into abbreviation mode. I'm not going to know what LCT is. Write it out. Limit comparison test. There are certain things that can be abbreviated, and everybody knows what they are. This is not one of them. Now, of course, it's the limit as n approaches infinity, and that will make infinity over infinity. You can try L'Hopital's rule like I did, but L'Hopital's rule does not work. It's one of those cases where it goes on forever. So instead, I have to get a little bit more creative. Think about this. You're heading towards infinity with your n. What's the difference between n squared plus 6 and just having an n squared? Not much. I mean, just 6, really. When you're that big, that plus 6 isn't going to matter. And if the plus 6 mattered before, you're cube rooting it, so it's even less of a difference. Really, that denominator is pretty much just an n squared inside. And if you take it to the 1/3, that's going to be n to the 2/3. So you'll have 5n to the 2/3 over n to the 2/3, which will cancel and make a 5. So again, on this, I just wanted to show you that L'Hospital's rule didn't work, but you can get creative to show that it is a positive finite number, which in this case was 5. Therefore, the limit comparison test works. And that concludes day number 2, our limit comparison test. We're going to spend one more day on this, or at least one more lesson on it, just as a quick review, working together. All right, see you then.